Okay, are you ready to start some simulations? This video is going to be focused on talking about how to build a queuing simulator. And actually, I've built the queuing simulator. I provided the code. It'll be linked in the handout. Um, but let's kind of dive into that code, explain what it's doing. For the homework problems, I'll ask you to maybe make a couple changes to it, but you're not going to have to start from scratch. So you're going to want to build off of what's already there. So before jumping into the actual code, let's kind of take a step back and think about um, what's going on in the code. We'll talk through some pseudocode. I would say it'd be with my undergrad in-person class, I often make them role play what's going on in a queuing system. And so it might be worthwhile to kind of think through what would happen in a queuing system of maybe customers arriving at a store and then being served and so forth. So here's the pseudocode, and let's talk through it. You're going to initialize the system with the initial state, which is usually that there's nobody in the system, but you could start the system hot in some sense of having some number of customers in the system at the beginning. And then you generate the next arrival time, okay? And then you go into a while loop. And while the current time is less than the end time, you're going to do the simulation. Essentially, we're going to have a continuous time clock throughout the simulation, and current time is going to keep track of what the time is currently. And then we're always going to, every time an event happens, we'll move that clock forward to the next event. Okay. So we're going to have kind of state variables that keep track of when the next events are. Okay. So first thing you're going to do at each sort of point in time is determine the next event, both when it is and what it is. Okay. Then once you've determined when the next event is, we're going to sample some metrics between our current time and our next event. Okay. So between now and the next event, the system doesn't change. And so we'll essentially record the state of the system in that time. And so I've set it up so that there's sort of evenly spaced sample points throughout. And so it might be that one sample point lies within the time window between now and the next event. It might be that more than one sample time falls within that time window. It might be that none fall within that window. You probably want to set it so that your sample times are close enough that you're getting several sample times between each event. But once you've kind of recorded some of your metrics, then you're going to have to handle the next event. And there's two possibilities for the next event. It can either be an arrival or a service completion. If the next event's an arrival, then there's two scenarios of what might happen. That person might arrive, and if there's an available server, they go right into service right away. If the person arrives and there's not an available server, then the customer joins the queue. Okay, so two things can happen on arrival. They can either go into service if there's an available server, or they can join the queue. And so thinking about states that we're going to need to keep track of, we need to keep track of who are the available servers and how many available servers there are. If the next event is a service completion, so someone gets done being served at the DMV, that person leaves and somebody else takes their place if there's somebody waiting in the queue. So we begin serving the next customer if there's someone waiting in the queue. If there's not someone waiting in the queue, then that server becomes idle. Okay, and so yeah, I always picture the DMV as my kind of working example in my head of what's going on. And you can kind of think of it whenever the person at the window gets done with the customer that they're serving, they'll kind of look up, they'll call the next number if there is somebody waiting in line. If there's not somebody waiting in line, then they kind of just go idle and they probably have other work to do. And then once we've handled the next event, then we can advance our current time to the time of that next event, resolve anything that we need to do with that next event, and then we go back into the beginning of the while loop and look forward to the next event. So we're essentially going one event at a time and always keeping a track of what's going to happen next. Okay. So let's jump into the code and I'll kind of talk through the code, and I'll maybe point out the few things that you might eventually want to monkey with or change up. So top part of this is kind of setting up a lot of the bookkeeping. So we got a start time and end time of the sampling. The start time of the sampling doesn't necessarily need to be at time equals 0. It can be sometime into the simulation so that you can essentially have a warm-up period. This is important if you want to get the steady state characteristics of the system, but not the transient phase. So you can kind of skip over the transient phase. End time is essentially end time of both the sampling and the simulation. Sample increment is how often you want to be sampling. So I've set this to go from 0 to 200, sampling every half unit at a time. Okay, and so I think I'm thinking of the time units as minutes, and so I'm going to kind of take a snapshot of the system every half minute. This sample time sets up a vector kind of sequence from start time to end time by that increment. And then sample size is just the length or how many times we're sampling. Here, SQ length and S in service, the S is kind of standing for sampled, are the sampled queue length and sampled number of people currently being served. We're going to essentially create vectors of length, the same length of the sample size. And for now, I'm going to fill them with -1s just as placeholders. We're also going to want to keep track overall of how many people were served, how many people arrived. At the end, these two numbers should be close. But if there's some people still in the system at the end of this simulation, then we're going to have more arrivals than services. Max served. This is mostly just to prevent us from going into an infinite loop. And so I've set it up to kind of have a max number served. You're going to want to set this to be bigger than the number of people that you actually or customers that you expect to arrive. Okay, so make sure to set this at a big number, and I'll kind of point out how big does this need to be. Well, if we're sampling for 200 minutes and our arrival rate is a half or one arrival every 2 minutes, then we can take our arrival rate times our end time, and that's going to be the typical number of people that arrive. And so a half times 200, we should expect on average 100 people coming. And then you want to go a couple multiples of that. And so probably double that would be safe. I went ahead and went 500, 5 times the expected should be plenty safe. Okay. So just make sure that this number is bigger than your arrival rate times your end time. Okay. So set the queue characteristics to have 2 servers. You're probably going to be changing the number of servers as you play around with this. The arrival rate is a half, so that'd be 1 arrival every 2 minutes on average. Sometimes it's going to be 2 arrivals in the same minute. Sometimes it's going to be 4 or 5 minutes between arrivals. And then this inner arrival time is a function that generates the next inner arrival time. And so it is just using an exponential distribution, generating one value of it from that exponential distribution with rate arrival rate. Okay. And so this is a function, and I just found it easier to make it a function, and we'll call that function anytime we need to generate another arrival time. Similarly, for service rate per server, we've got a service rate of 0.3. So on average, we serve 3 clients every 10 minutes or 3/10 of a client every minute. That maybe doesn't make the most sense in my head. One thing to note here, if we want to compute our utilization factor, that's our arrival rate, also called lambda, divided by S times our service rate, which is often called mu. So in this case, we got 0.5 divided by 2 times 0.3 or 0.6. So 5/6 is our utilization factor, which is pretty high utilization factor. And we'll see how that affects our queue when we run it. And the service time also is a function that generates the next service time. Otherwise, a couple more setup things, and then we'll get into the loop. We're going to start the current time at 0. Note that the start time for sampling could be after the starting current time. In service is going to be a vector of trues and falses, one for each of the servers. And it's true if that server is in service, serving a customer, and false if that server is not serving a customer. So at the beginning of time, none of the servers are in service, so we start off with all falses. In queue tells us how many people are in queue, waiting in line. And so at the beginning, nobody's in service, nobody's waiting in the queue. Now, in order to make some of the code work, when I'm looking for the next time, I need to be able to put in a time for the servers who aren't in service that's not going to be accidentally mistaken for the next time. And so I've made it so that any servers that are not in service, their next time to complete is after the end of the end time. And so I did end time plus 1. Okay, this is mostly just a little bit of a trick so that I have a kind of placeholder time that won't trigger for servers that are not in service. Okay, arrival index, I'm going to have this next time vector. The first S places in that vector, so the first S slots, so in this case there's 2 servers, first 2 slots are when those 2 servers will finish their next service. Or if they're not in service, it's going to hold the placeholder time. Okay, and so to begin with, the first 2 servers are not in service, and so I'm putting the placeholder in the first 2 slots. And then the last slot, which is going to be slot S plus 1, holds the next arrival. Okay, and so at the beginning, it's going to be current time plus an inner arrival time. So here's how you can use that inner arrival time function. It will generate the next arrival. Okay, so next time is going to be a vector. The first S slots are for the services, and the last slot is for the next arrival. Okay, so that's all just setup. There's a lot of kind of moving pieces in this queuing simulator to kind of keep track of. I encourage you to kind of step through the code, look at what each of these are, look at how they're changing throughout the simulation. Now we jump into the while loop. So we're going to run the simulation as long as current time is less than end time. Okay, once current time reaches end time, we're at the end of the shift or at the end of the simulation. And we're also going to limit it to keep number served less than max served. So this is just a way of preventing us from sort of an endless loop. And so because we know that we're always going to add one on every time someone arrives, actually, maybe we should have this as max arrived instead of max served, but kind of things you think of after the fact. This is maybe just a way to prevent an infinite loop. Okay. So first thing we do is figure out what the next event is. And so I look at my next time vector here, and I find which .min. Which .min tells me which of the next times is the minimum. And so if which .min is one of the first 2 in this case, then I know that the next thing is a service completion. On the other hand, if the next event or which.min gives us the last entry, then I know that the next event is an arrival. Okay. Then once I figured out what the next event is or when the next event is, then I'm ready to sample. So I'm going to look at, find all the sample times that are greater than the service time and less than the next event time. Okay, and those are going to be my current samples. These are actually, which will give me actually the indexes that correspond to those samples. And then I'm going to record in queue to kind of record how many people were in the queue during those samples and how many are in service during those samples is going to be the sum of in service. In service is a vector of trues and falses, but the fun thing about if you sum a vector of trues and falses, that will count the number of trues, which will essentially tell me how many people are in service or how many servers are in service. Okay, then we're ready to advance to the next time. So we can move current time up to the next time of the next event. Okay, then we need to kind of resolve that next event. If the next event is an arrival, that would happen if next event is equal to the arrival index, which is that last index of the kind of next times. Then we had an arrival and we need to process that arrival. So then we'll say, we'll update the number that arrived by 1. We'll update the arrival times by putting the current time in for the current arrival. And then we've got 2 options. Either everybody's in service or everybody's not in service. And so in service all, ask the question, is everybody in service? And if I put an exclamation point, that would mean is not everybody in service, kind of, which means that there are available servers. So this is what this next chunk of code is what happens if there are available servers. If there's an arrival in the available servers, then I find one of those available servers. So I look at which min of in service. Essentially, it really doesn't matter which server I assign it to, but I'll always assign it to the first available server, which would be the just kind of first in the order of the listing. Then I put that server into service. So update that server's in service to true. I generate a service time for that server. Okay. And let's see, service times. Oh, and I kind of record the service start time as the current time and the service finish time for that person as this same next time of the next server that I just created back in this line right here. Okay, so these 2 lines are just bookkeeping and kind of tracking things over time. Okay, if there are not available servers, then I jump down to here. And if there are no available servers, then I add that person to the queue. So I just add 1 to the queue. Either way, I'm going to generate their next arrival time for the next person and put that in the arrival index spot of the next time. Okay, so that's what to do if there's an arrival. Now we need to deal with what do we do if there's a server finishes with a customer. Then we can increment the number served because we completed a service. And then there's 2 possibilities. If there is a queue, then the next customer in that queue goes to the server that just finished. And so we'll reduce our queue size by 1 because we're bringing somebody out of the queue and into service. We'll generate a service time for that person that went into service, and we'll, essentially generate the service start time for that person who just went into service and the service finish time for that same person. Okay. On the other hand, if there's no queue and a server finishes, then that server who finished goes idle. So that server's in service goes to false, and we set their next time because they're not doing anything. They're not currently serving anyone to our placeholder time that is after the end. So we kind of push it out so that it won't trigger as being the next event. So, and then that's the end of the simulation. Okay, so then kind of these close off some of these ifs as well as the while. Okay, so that's the simulation. Let's look at some of the results that we can get out of a simulation. So here we can plot the queue length over the sample times. And so here are the times between 0 and 200, and we can see how the length of the queue changes over time. So what's pretty typical in these queuing systems is you'll have stretches where there's not many people in line, but then kind of you'll get a cluster of people arriving close to each other, or maybe some consecutive services that take longer than typical, and you'll see the queue grow. And kind of, yeah, things can spiral out of control with these queuing systems and be longer for a while and then maybe drop back down. And so here's the queue length over time. There's some points in time where there's as many as 10 people in the queue. Let's look at the number of servers who are in service. And so over time, we have 2 servers. So these circles down here are when there are 0 servers working, which means they're all both idle. Here are the times where there's 1 server working, 1 idle. And we can notice with this system, actually, most of the time, both of the servers are working. Neither of them is idle. Okay. Overall, the numbers served in this case was 101. I said on average 100, turned out to be pretty close. The utilization factor is sort of the average of whether they're in service or not divided by the number of servers. And in this case, we got a utilization factor of about 87%, which is pretty close to what the kind of theoretical value would say. We can look at wait times. Now, these graphs up here are over the sample times. These next graphs are over the indexes of the customers, okay? And so we can look at the wait times in queue, and we can see first couple customers didn't have to wait at all, but by the 6th, 7th, 8th or so customer here, they had some longer wait times. I think the 20th customer around there, they had to wait 10 minutes in queue before being served. Customers around the 40th customer didn't have any wait times, but around the 60th, they had some pretty long wait times as well. And so these peaks in wait times correspond to the places over here where the queue got long, okay? Our average wait time in the queue was about 4.5 minutes. And the total wait time, which is both in service and in queue, here's that distribution over time. You can kind of see the same bumps in there. Whereas some people had no wait time in queue, everybody has at least some service time. And so you might have some low times here, but none of them are exactly 0, even if they didn't have any wait time. And it looks like the worst person was right around the 60th person to come in, and it looks like they had a total time up over 20 minutes from when they came in to when they were able to leave. Okay, note that the way I computed these wait time totals was when their service finished minus when they arrived. Okay. And similarly for the wait times in queue, I took when their service started minus when they arrived. And so that's the amount of time that customer was in the queue. The mean wait time total was about 7.8 minutes. Yeah. One thing I'll point out is the difference between the wait time in queue and the wait time total is the average service time, which will be directly related to the value of mu. Okay. And that's really kind of my explanation or walkthrough of the queuing simulator. For your homework, I'll have you run the queuing simulator. I'll have you run it with kind of different number of servers. And then I'll have you also experiment with different costs. And so at this point, I've just sort of got the metrics in here. But what you're going to need to do is add at the appropriate places where costs are incurred. And so kind of keep in mind sort of the comments of what each part of the code is referring to, and use those to kind of target where you introduce the costs into the system. So yeah, the homework will have you modify this. Don't hesitate to ask for help if you're kind of lost in this code and need to talk through it. It was not simple to code up. It was a fun coding challenge, but yeah, definitely a level higher than most of the simulation challenges that I'd done before. And so pretty good challenge though. That's it for this video. Next video, we'll talk a little bit about the exponential distribution and why I love it.